Hello, welcome to CM Videos. My name is Dr. Michael Okreke. I'm making yet another video on the representative volume element modeling of different architectures. And the one that we're interested in modeling today is a bidirectional composite. And they are bidirectional composites in the sense that the laminates are oriented in a 0 degree and a 90 degree direction. So they are orthogonal to themselves. At the end of the simulation, these are the kind of results that we will get, and these are basically unidirectional axis deformations as well as shear axis deformation. We also went ahead to generate the stress strain plot from these different simulations. If this is the kind of content that you like, please do subscribe, like and share so that when content like this are made, you'll be the first to see it. So let's jump ahead and begin the modeling. So the first thing that we're going to do is to look at the outline of what we're going to do today. So basically, I want to introduce bidirectional composite just for sake of continuity, especially for those who don't already understand about bidirectional composites. And then we look at setting up the model in ABAQUS. How do you actually set up this RVE simulation within ABAQUS? And then we now go on to review the simulation result. This review will be based in terms of the contour plots, what is unique about the deformations that we're seeing, and then finally I'll show you how to extract stress strain data from these different simulations. So for understanding a little bit about bidirectional composites, so I've taken this data from this publication, which is basically showing a micrograph for a bidirectional composite. And so what we see here is that there is a 0 degree laminate and a 90 degree laminate. And this is typically how a bidirectional composite would look like if you look at it under a microscope, and the orientations will always be orthogonal to themselves. And then the next thing we can see is how do we identify an RVE for such a system, because in the end we are using this modeling approach where we are trying to use a representative volume element representation for it. So if you think about this, so if I isolate that region, so this could be my potential representative volume element for this bidirectional composite. And if we zoom in closely, you find out that this could be the arrangement of the representative volume element, where you could see the matrix as well as the fibers, which are kind of in those dark circles. So they represent the fibers oriented in a 0 degree direction and a 90 degree direction. Okay, so for this specific simulation that we're running, we're going to work with a stacking sequence, which is basically the arrangement of the laminates made up of a 0 degree laminate, a 90 degree laminate, another 90 degree laminate, and a 0 degree laminate. It's really important that these laminate arrangements are always balanced, so they are symmetric about the center line, just for balance of mechanical properties, and so you don't end up having buckling or curving. So that's what we're going to do with this. So the first thing is, in terms of this RV modeling, you need to isolate the metrics, in which case this is the arrangement of only the metric system. You add it with the fiber. So here I've distinguished the 0 degree fiber, which are basically the fibers that are in purple shape, and the other degree fiber, which is the 90 degree fiber that have a cream shape in them. And when we combine those two together, then you end up getting the complete BD composite, which is what we see here. So this is the identified representative volume element for a system like this, which is made up of a 0, 90, 90, and a 0 degree stacking sequence for a bidirectional composite. Okay, so in terms of the material that we're going to be working with in this video, so I'm using an A-glass fiber. This is the kind of material that I've used in most of my videos on RVE modeling. Again, if you're interested in RVE modeling of a unidirectional composite, please look on the card. I've put some videos about how you can actually do this for a unidirectional composite. So in our system here, we've got E-glass fiber with a volume fraction of 30% and a polypropylene matrix with a volume fraction of 70%. So that's the material that we're going to use. Then the next thing is, how do we actually create the virtual domain that we need for this modeling, because this is kind of where the difficulty lies in this sort of modeling. So remember, we're still working with this stacking sequence of 0, 90, 90, and 0 degree. And just to kind of illustrate that, so we have a laminate that is oriented in this 0 degree direction, as we see here. And the next thing we have to introduce another stacking sequence, which is oriented in 90 degree direction. And because I want it to be symmetric, so in which case there is a mirror image of this 0, 90, so that means the next thing we'll have will also be a 90 degree laminate. And then finally, we also have a 0 degree laminate. So that by the time you apply loading on the system, like I said earlier on, there is not a curving effect due to the imbalance in the stacking sequence arrangement. So this is typical for most composite materials. So this is a schematics of the system that we are trying to model in this video. Now, if we move on more, the case study obviously will be based on a BD composite that I've already spoken of earlier on. So these are the typical dimensions that we're working with: a 0 and 100 micron units, cubic represent the volume element. So I'm going to show you how this can be created within ABAQUS to help us build a model. The other thing that we need to note is that our fiber system here has a dimension of 100 microns. A-glass fiber will typically be between 120 microns in diameter. So I'm using 100 microns in diameter for the E-glass fiber in this case. So in terms of generating the virtual domain, I've taken liberty to create it using montcarlgen. So this is a software that I've written. Again, if you want to understand how it works and the principle of Monte Carlo generation, there is a video that I put on the card that describes how this can be done. Also, if you want access to the videos, again, watch out in the link for how to get hold of the software, which is for montcarlgen. So remember, we're working with this stacking sequence of 0, 90, 90, and 0 degree direction. So montcarlgen will generate a random arrangement of fiber in a 0 degree ply, which is the base ply. And then the next thing is it will also create a 90 degree arrangement. Okay, so of course the orientation of this will be different, but just bear in mind with this, it creates them all as unidirectional. But when we assemble them, we're going to have to twist the 90 degree into a 90 degree direction. So, but the other thing you need to know that there are two plies here, one there and another there. And then finally, we'll end up with the third case, which is also a 0 degree ply. In terms of their dimensions, the base length will be 100 microns and the height will also be divided in blocks of 25 units, micron units, to make up the overall expected 100 micron unit length. So in the end, we are going to get a cubic arrangement. After we created this, it will be extruded depthwise so that we'll have a cubic arrangement of 100 on the length, 100 on the height, and 100 also on the depth. So this is what montcarlgen will do for us. It will create these three arrangements, and then, of course, because we're looking for the 90, we're going to rotate it so that it will be a 90 degree ply, but I will show you how to do that when we get into ABAQUS to set up the model. The other thing that we need to think about is how montcarlgen workflow works in terms of creating the framework for us. And it's quite simple. montcarlgen will output 3 Python scripts. The script 1 will be for the 0 degree laminate. The second script will be this assembly of 2 90 degree laminates. And the third script will also be for a 0 degree laminate. I made a decision that I wanted the 0 degree laminate to have different random arrangement of fibers in them, because someone could say, why not just use script 1 the same, because it's the same fiber arrangement. However, I decided to have a little bit of flexibility in terms of just create random arrangement for this fiber and this fiber, because that's how it will be in practice. Now, the RVE design, of course, one of the questions is how many fibers will fit at the 0 degree laminates. Think about the 0 degree laminates. We're going to work with this equation, which says that the volume fraction is the number of fibers times their cylindrical, the volume of the cylinder divided by the length. The heights are exactly the same, so we end up with a relationship like this. And if we calculate it, we find that you're looking at only 10 fibers for the 0 degree laminates with a height of 25. Now, I've made a choice for the 90 degree laminate to bundle together those two laminates. So we end up having 225 units laminate because the orientation is exactly the same. So what do we have here? So we end up having a 50 micron height, and then the overall length, number of fibers required here will also be 19 fibers. So that's the design. Now, in terms of the loading analysis, which is basically the case studies, the simulations that we're going to run for this. If this is our RVE, so we want to first do a bulk of uniaxial simulations, of which we'll have case 1, where loading is in this x-axis, case 2, loading is in the y-axis, and case 3, where loading is in the z-axis. So these are the 3 uniaxial simulations, and of course we'll also have shear simulations, just to show the depth of what this RVE modeling can give to us. And so we'll also have a shear deformation on the xy plane, a shear deformation on the YZ plane, and a shear deformation on the ZX plane. So 6 different simulations that we're going to run to show us, how RVE modeling of a bidirectional composite would work out. At the end, we're also going to create stress strain data, which would help us get some kind of quantitative data about this RVE modeling. So if this is the kind of content that you like, please again do subscribe to this channel if you have already done so, if you have not done so, and click the bell button so that you get notifications of when videos like this are made. So we're going to go straight to ABAQUS and I'll show you how this modeling works. Okay, so the next stage of this video is on how to set up this model actually within ABAQUS. So this is what I'm going to show you how to do in this next section of the video. And the most important thing that I really want you to bear in mind that we're going to use a script to do this. So remember what we tried to do here was to basically look at this stacking sequence of 0, 90, 90 and 0. And the two 90-degree fibers are basically going to be one system, and then we've got the 0 and the zeros on the two outside. So we need a script for the 0-degree base, the 90 which are the middle plies, and then the 0-degree at the top. So here we are. This is a script that we're going to use to actually do this. So first I've got a script which I've written. Again, these scripts, the three of them, the UD 0-degree base, UD 0-degree top, and UD 90-degree middle, they are all available in the download section of this video for those who are interested. Again, you can get hold of this and you can work along with me. So with the first code, Ctrl-A to select and then Ctrl-C to copy. Then I'll go here and paste it right here. So we'll run through all the code and generate the result that we are kind of interested in. All right, so this is the first case, which is a 0-degree ply, and it shows us that. So we'll go back to the script, get the middle ply. So I'll copy that, go back and paste it right at the base. It will run through and extract similarly what we have, which is a UD composite for this middle ply. And then we'll do the same for the top ply. Okay, so it will run through on the top ply and again extract the three results that we're looking for. So if you see here, you've got the three cases all here. So what I'm going to do is that I'm going to have to create a model, use this first case, copy and use it as a basis for our BD composites as a case. So we'll work with that. This is fine, and then I can delete that. So then I now need to bring in the top and the middle, but the best way to do this is to actually export them as a part and then bring them back into the BD composite. So at the moment it's a different model sitting on a different, for it to be translated and brought back into the BD composite, it has to be exported as a part. So I export this as a part, so I could call it UD 0-degree, top part, okay, something like that. So I've already done the export, so this is okay. Release 24 is fine. Anything from 2016, I'm using an ABAQUS 2020, so this is okay. So we'll do the same for the 90 degree. So I'll find the 90-degree arrangement, export it. So you give it a name, okay, maybe 0-90-degree. Okay, you could call it middle. Okay. And again, I've done the export previously, so release 24 and later I'm using 2020 this, okay? So this is done. So once we have exported them, you can delete this part because you don't really need them anymore. Now we need to import them into this particular model that we're interested in, okay? This BD composite model. So I'll do file import as a part. So you find where it is located. I know where it's located in my model. So the first of them will be the middle part, so which is 0-90-degree middle. Okay. So the part name I'll keep. I combine them into a single part because I want everything to be one single component. And then that's really about it. Okay. So what you'll notice that within the part module, you now have the 0-90-degree. You've got the UD composite as well for the base, 90 as well. Okay, so you do the same for importing the top. So the top part or top model, whatever you call it. So again, import it as a single file. So it comes into the mid system. So we've got all three of them. So this is the base system. These are the other two cases. So what I'm going to now do in the assembly module is to create instances of all the three. So already we have an instance. So if you open the instance window, have an instance for the base system, so we're not going to worry about that. So we just need to create instances for the top and the middle. Okay, so that's there. So they're all kind of jumbled together with the same origin. So we need to rearrange them and put them in the positions that we need to be. So I'll translate the middle section, the middle part, from the origin, which is here, to that point. Okay, so that gives me the middle, the case for translating to the middle position. You can see it here. So I'll do the same translating, select the top part from the origin where it is, obviously, to the top where I want it to be. So if I get all that together, so that's that. So what we will have now is a complete arrangement with a 0 degree ply, 2 90 degree plies, and another 0 degree ply, in the way it's supposed to be. Okay, so we've got them all set up. Again, if we switch them to part instances, it could show you that they are actually different parts in the way they need to be. So while it's still here, we need to rotate the central one so that it goes into a 90 degree, because at the moment it's looking like a unidirectional composite. So we need to rotate the central one. So the way I would rather want to do, there are different ways you can do it. I'm going to use the circular patterning, option. So I'll select this instance, which is what I want, and already, if you look, it's creating a circular pattern in the way we don't want. So I'll reduce it to only one patterning. I just want one pattern that I'm going to work with, but I'm going to rotate it on a different axis because it's rotating about the Z axis in this case, which is not what I want. So I want to rotate about the Y axis. Okay, so I'll select that. So you see it's rotated it into, so we now have a different pattern, a different instance, which is the instance that represents the 90 degrees. So we need to move it from here into this location, but we need to delete that particular model. So that space becomes available, and then we can translate it from where it is, from that corner where its origin is, to this corner. All right, so we now have a complete setup of what our model should look like with 0, 90, 0. The 290 plies in the middle. Now at this stage we can merge. So this becomes my BD Composites assembly. Okay, so I want to merge it by geometry, separate the original instances, and remove every intersecting boundary, so I would have the whole system as one. So continue, and then I want to select everything here, and that gives me a complete model. Okay, so the good thing is that at the top end here we also have a complete model for our BD assembly. So from henceforth we'll be working based on this BD assembly. Okay, so we need to do a section assignment. Double click on that. So untick this. So I want to select the matrix alone. So I'm going to matrix of fiber. I remove selected, change this to cells, select that, and click done. So that lists only the fiber. Then I can select the fiber alone. Okay, so double click on instance, select the fiber alone, done, and then that becomes my A-glass fiber section. Now I invert that, leaving behind the matrix, select the matrix alone, done, and then make that polypropylene matrix. So we can then resume all that, switch to material module so that we can see it looks right. So the fibers in their position, the matrix in their position. So we have this model, and then we can mesh it. So if you double click on mesh, it's recommending so a seed size of 10, which is okay. So I'll select how I want to mesh this model. I want to probably use a tetrahedron to mesh it. And then when you mesh the model, so that's a good mesh. By all means, you can go ahead and mesh more. It's coming up at around 108,000, nearly 109,000 elements. For this case, it's all right. It's not super fine mesh, but it's an acceptable mesh. So we can work with this mesh for our modeling. Okay. Obviously, the next thing we need to do to make sure that our materials are right, because we've done a material assignment. So E-glass fiber, I'll provide the properties for E-glass. So this will be 73 e to the power 9 and 0.2. It's an elastic material, so we're not bothered about that, about plasticity. So for the metrics, so this will be 1.308 e to the power 9 and 0.4 for the Poisson ratio, and the plasticity value will be 40 e to the power 6 and 0.0. Of course, you could have also damaged models for it, but we're looking at only a simple case in this model. So the next thing we need to then do here is to think about how we're going to set up the model. Okay, maybe I can create a step and call this my loading step. It's a static general, that's fine, everything by default. Now, so if we go back to here, which is the BD composite, I need to create different sets that I'm going to use in terms of how I apply the loading on the model. So double click here and create. Okay, I'm going to do an X front set, X front, and I'll probably use a nodal set to do that. So I'll switch this to angles and then hover on the front, so I select all the nodes on that front face. Okay, and then we'll do the same Z front based on node alone. You hover in the front, select all that. So we do the same for all three cases. Okay, so we've done it for all the 6 faces. We can cycle through. So this is X back, X front, Y base, Y top, Z back, Z front. So we're happy with all that. One thing else that we probably need in the assembly module is a reference point, so that we can use that apply our load. So you can query any point in the model. So I'm interested in this point. So if I query that, it's coming up as 100, 0, 100. So then I can create a reference point there. My reference point will be at 120, 0, 100. So it will just be 20 micron units away from that point. So then within the assembly module, I can create a set. So my reference point set. So I'll select that. So this is fine. So I've got a reference point set. And we have most of the things that we need to get this model going, except the information around boundary condition. So I will double click here, and I'll say, okay, my X back would have a roller support, displacement based. So select the set, which is X back, highlight it as a mesh. Okay, that's the right case. It will be constrained in the one direction. Y base roller, constrained in the 2 direction, and Z back roller. It will also be constrained Z back in the 3rd direction. So here we now have a boundary condition that models that applies the deformation, the restraint on this. So we can then use this as a case for setting up the individual cases. So if I do copy here, so the first one here will be extension. So I want to set up a model with extension alone. So if you put that extension, go to the boundary condition. So we can then switch here and say, okay, my extension load, or just call it load. The loading step here would have to be applied at the reference point. So I use my reference point to apply my load, and it will be in the 1 direction and 10. How do I get 10? Because I'm applying a 10% strain. The edge length here is 100, so 10% of 100 is 10. So 10 micron units is the loading that I'm applying on this domain. So I'm applying on this reference point, but we need to connect this reference point to the X front face, and we use our constraint to do that. Constraint. So I'll use a star equation for constraints. So if I open this up so that I can see everything that I'm doing. So the first one is this, and X front is what we need in the one axis minus the displacement of the reference point still in the one axis. So that means I'm now linking the behavior of this reference point to that front face. So if there's a loading displacement here, the front face will also follow suit. And this is how we're applying loading on this. The advantage of this is that then we can also track the history output. Instead of tracking the whole history of the model, we'll track the reference point history output. So it will only be a point in the model, but then it's a kinetically coupled point to the whole system. So this becomes my reference point, and RF1 and U1 being the displacement in the one direction and the reaction force in the one direction being the x-axis. So I'm tracking the history of this reference point, and because it's kinetically coupled to what's happening on the front face, then it's translating the information of what's happening in the model to that point. So this is fine. So I then click a copy and then do Y tension. So with the Y tension, every other thing will remain the same. So my loading will be different. So the load I would apply will no more be in the one direction, it will be in the Y direction. However, my constraint will also have to change. So the constraint equation would no more be on the x front, but rather on the y top, and the degrees of freedom will be 2 for the y direction. So we need to also change the history output for the y case from one direction. So that's my y tension. So if we then copy and do z tension, so the same thing we did before, our loading will be different. If we double click on our load, it will move from the y-axis to the z-axis, okay, which is fine. However, my constraint will need to change. So if we change the constraint here, the constraint will be in the third direction and it will be on the z front. So we're applying it on the z front. We need to also change the history output there to reflect the fact that we're now interested in what's happening in the third axis, which is the z-axis. So the shear cases are slightly different and we have to handle this in a different way. So we'll copy this. So I'm going to call this xy shear. Now with the xy shear, if you open it up in the boundary condition argument, so what I'm going to do is my loading would have to be on this face but in the y direction. So I'll select that load in the y direction there. Now it's still a reference point, so we have it here, it's applied there, but we need to instruct it to be connected to this face, however, in the y-axis. And that's where the constraint equation comes in. So we'll double click on the constraint equation. So the one direction, x front is okay, but it's moving in the two direction. Now we could also go back to the history output for this shear case. Because we are moving in the two directions, so this is no more one axis, it will be a two axis case. And then in terms of boundary condition, because this front needs to be held, so we create an extra boundary condition. So our extra boundary condition, so it's x front roller. So it's an initial boundary condition and it will apply on the front face and it's going to constrain in the one direction. So that it doesn't move in the one direction, however, only slides upwards. Now the x back would have to be renamed to x fixed, and that x back would have to constrain in xyz direction. So you hold it firmly there and you slide at the front. All the other bits, yz and y base, will have to be suppressed. Okay, so we don't need those. So that's that for xy shear. So why not do this? We create a copy of the y tension to give you yz shear. We look at the loading attached to it. So the loading will now have to be on the top. So the loading will be, however, yz means we are moving in the z direction. So I'll switch this to the z axis. And I would like to add a minus in front because what I want is my shear to be pushing that top plate backwards. So the constraint equation will still be y top, but it's moving in the z axis. The history output will no more be a 2 history output, it will now be a 3 axis history output. Then we think about the boundary condition. The y planes are the planes of interest, so every other thing away from that will not be important. So we suppress those. Now this yr will need to be changed, y base out, y base fixed, so that we could constrain it in x and y direction to hold that base firmly. And then the top end will need to constrain it in the y direction. So this will be y top with a roller support. So initial boundary condition, so y top, and then we'll constrain it in the y axis. Now the last case is the Z tension, which I will copy and use for my ZX shear. Okay, so with the ZX shear, I'll go straight to the load type, make sure my loading looks correct. So my loading in the ZX means Z plane, but in the direction of X. So again, I'll put a minus there because I want the shear to be outward to push out. Okay, so this is what you see here. So that's correct. Now we are only working with the Z planes, so the ZX will be the Z planes. So every other thing away from that will have to be suppressed. So leaving only the Z reaction, the Z back I would change to Z back fixed, and it would have to have constraints properly set. Then I need to also create another Z front roller, Z front with a roller support with an initial boundary condition, Z front, and it's constrained in the Z axis so that we have a freedom to move in the X direction. So that's how this boundary for the shear cases would have to be. Now constraint equation, So the Z constraint equation will still be on Z front, however, it's moving in the one direction. So our degree of freedom of interest is in one direction. And we can then look at the history output to make sure that we are asking for the right kind of result. So it will obviously have to be the one reaction force, one axis reaction force or displacement, which is the x-axis. So those are the 6 models that we've set up. So you can see how we set up this model. So we can then go ahead and create jobs for them. So for example, the first case would be the composite extension or something, and select and submit. I'm going to submit all the model, run all the model, and then show you the result. Okay, so we finished setting up all the models, running them, and we've got the results. So if we then look at the results for each of them. So this is the first instance. So this is the extensor deformation case. So this basically tells us the extensor deformation results that we are extracting, and this is in terms of the von Mises stress. So if we switch it to a plastic strain, it gives us the idea. And you could see what's happening with this simulation. So you're pulling in this X direction and the system is protruding out. So these fibers are resisting the movement, this matrix region. So you have this combined combined behavior. And this is typical of a bidirectional composite, and it shows you some interesting results. So if we then look at the next case, which is the Y tension. Now, remember what's happening with the Y tension in this case is that, if we go to plastic strain, is that the fibers are oriented in those 2 directions. As you're moving up, you're pushing in the Y direction, those fibers actually do not offer much restraint, much resistance, except the fact that, during the Poisson effect, they may resist movement. So there's an enhancement of properties, but mainly, this is a problem with laminated composites. On the outward plane in the y-axis, or in this case, or what we call the z-axis, the fibers do not actually add much constraint, much contribution. Okay, it does provide some reinforcement, but not significant. Okay, so this is what we see with this. Again, if you animate that, you could see what's happening. So this central region is contracting and the top end is moving. All right, so let's look at the third case, which is the Z tension. So the result from the Z tension. Okay, so Z tension is similar to the first case, which is the X tension, especially if you again animate this. So these 2 fibers are taking most of the loading, as you could see by the values of their stress history, and all the other bits are not really doing much in this case. So if we look at the plastic strain as well, it gives you a picture of what's happening. So again, those 2 are pulling and these fibers are resisting the motion as well. So that's providing significant reinforcement to the model. So the X and Z plane are properly reinforced due to the effect of the fibers. The Y plane in this case is not really that reinforced. So what about in the shear cases? So let's do the XY shear. So look at the XY shear in the shear case. So again, if you think about what's happening here, especially let's try and exaggerate this further, maybe to 3. Okay, so what's happening with the shear cases is that you're shearing upwards in this case. If you go in this plane, so you could see there's a shear deformation going on in the model. You look at the plastic strain, so the fibers are basically being moved around as the system shears up and down. They again do not really offer significant reinforcement. It do offer, but not as when you're loading in the main fiber axis. So clearly the back end is fixed, so these fibers are basically being bent and rotated. And so this is what you see with the XY shear plane. Now we look at the next one, which is the YZ shear plane. So the result of the YZ. So again, a similar kind of behavior. Remember, what we wanted is to push the system back. So you could see that the top end is being sheared and the bottom end is not. So you could look at other planes. So this is a plane. So if you animate this, so you can see what's happening here. So the top end is being sheared and the fibers are contributing, again being wobbled around, but not in that dominant uniaxial case. They do add reinforcement effect even in shear, but not as dramatic as you would expect for the first X and Z directions. All right, so and the final case is the ZX. So the ZX is where you're shearing towards the X axis on the Z plane. Okay, Z axis on the Z plane. So if we animate this, okay, no, so if we go back and animate it, So you could see what's happening. So the front end is being sheared outward. There's an interesting distribution in terms of the stresses in the fiber during this shear. So basically, in principle, what's happening here is that these fibers are being, bent. So there's a buckle. They are forced to buckle according to this axis. So if we then look at the plastic strain, you could see which fibers, what's happening around the fiber. Again, there's some reinforcement effect, but not as dramatic as in the first X and Z direction. So that's what we will see by way of reviewing the contour plot and learning something from the deformation. But what will really be interesting is how we can actually do this in terms of generating the stress and strain data for these graphs. So the last thing I want to talk about is how to extract stress and strain data. So let's go back to the first case, which is the extension case. So we want to extract stress and strain. So you need to click on this create XY data option. So as a history output, because when we set up the model, we asked it to record certain history output values. And our history outputs are basically the reaction force in the X direction and the displacement in that direction. So we plot them. So what is showing us right away is a linear behavior in that X direction. There's no non-linearity. So the fiber is dominating the behavior of the system. So it's very, very strong in that direction. So there's a linear behavior both in displacement and stress, or force in this case. So, but we want to use that data. So plug in tools, Excel utility, from current plot, click OK. So what this will do is we'll take this data and export it into Excel. So we take that data here. So I'll just copy all of it, Control A, Control C. So this is time, this is reaction force, time, and displacement. So if I copy all of that, copy. Now I've prepared an Excel script that we are going to use. So this is the Excel script that we're going to use. It identifies the RVE type, the length is 100, the width is this, height is that. Then there is a way to calculate Young's modulus, calculate the effective strength of this material. So if I paste this data in here, so already it calculates the Young's modulus by taking the slope in the first linear section of the model. Okay, and what is the strength? The strength is basically the maximum, absolute maximum value on the y-axis. So it's coming up at 1100 in that axis. Okay, so this is what we get for this situation, for this particular system that we are working with. Okay, so we divide it by the length associated with the system. In the Y tension case, so if I switch this to the Y tension case, okay, which is this instance, so again, I'll look at the history outputs. The history output will be based on RF, so the RF2 and U2. So we'll plot that. So what we see here is that there's a non-linear behavior, elastoplastic behavior for this force, and the displacement is uniform. So file tools, Excel utility, from the current plot. Again, what will it do? So what it will do is it will create this table. So we'll copy that. So this is the data. So I'll go back to my head and then I'll paste that information here. Okay, so it shows us the elastoplastic behavior in that Y plane. Remember I said the Y plane is a plane where there is really no reinforcement at all. And so the lamination will happen on that plane, so to speak. It's a weak plane. So we do that for the Z case. The Z is also a dominant case, which is Z is the other axis, like the x-axis, and then all the shear cases, their behaviors. So in the end, we'll end up with a result that look like this. Okay, so which is effective properties for the system for the X tension case, Z tension being the quite dominantly linear cases, and then of course we now move on to the Z, the Y tension, which is a weak zone, and all the shear cases. So what I've done here is to put also those weaker cases of Y tension and the shear cases all together to get some kind of result as to what we need. So this is what we're going to get, and then at the end you'll also look at the stress, the effective properties that we generate from the model. So again, 11, 12, approximately 12 gigapascal in that plane. This effective strength could be less depending on incorporating a failure model to the system. But the Y tension or the delamination axis basically is not high enough. And then the shear cases are all comparable, in that. So this is typically the kind of result that you will get from this kind of simulation. Yeah, so this is what I've been able to do. So I've shown you how you can actually set up this model. I've also shown you how you can run it in ABAQUS, generate some stress strain data, and draw some kind of conclusion. So if this is the kind of content that you like, please do subscribe to this channel so that when content like this are made, you'll be the first to see it. Thank you for your interest in this CM video channel, and see you in the next video. Bye bye.